Good afternoon, everyone, and welcome to today's session, Scaling for Success in Today's Data-Driven World. I'm Dave Rubenstein, Editor-in-Chief of SD Times, and I'll be your moderator today. Before we get started, I have a couple of quick announcements. First, today's program will be followed by a live Q&A session, and you can ask a question at any time during the presentation by navigating to the question area of the control panel, typing in your question, and hitting Submit. And during the Q&A segment, we'll answer as many as time allows. Secondly, this program is being recorded and will be hosted on sdtimes.com in the next day or so, and you can watch it over and over again to your heart's content, or invite a friend. Anyway, as we've been reporting in SD Times, the explosion of data within organizations has presented enterprises with both opportunity and enormous challenge. We know that gaining insights into the data that's being collected can help businesses make better strategic decisions and gain competitive advantage. But there are challenges. Key among them are scalability and downtime. What do you do when the system gets overloaded and fails? The costs associated with that downtime are, as they say, huge. So with us today to talk about solutions to these problems are Matt Davis, Senior Site Reliability Engineer at OpenX, which is an advertising technology company. Matt's an expert at running some of the largest data clusters on the planet, and he likes to combine art and music philosophies into his approaches for managing complex computer systems. Also joining us is Heather McKelvey, Vice President of Engineering at Basho, the makers of the React Distributed NoSQL Key Value Store. Heather has more than 20 years of experience leading and managing software teams. She was the CTO and Senior Vice President of Engineering at GoGrid, where she led architecture and development of cloud services, inclusive of compute, SDN, storage, and network services. In her career, Heather has also worked at Mashery, Netscape, Compact, and Ingress. Okay, let's get the program started. So to kick things off, here is Heather McKelvey. Heather?
Thanks, Dave. I'd like to kick things off here by talking about the data explosion that we've all been seeing for the last couple of years. In 2010, we actually were storing approximately 200 exabytes. And every 2 years, the amount of storage for data is going up. It's doubling. In 2015, the estimated amount of storage was 1.6K of exabytes. So the explosion of data, the ability to store that data, the ability to manage that data, has grown immensely over the years and only continues to grow. In fact, between 2010 and 2020, it's expected to grow 50-fold. So building out data platforms has become key for many people in being able to make the proper business decisions going forward. As we have the Internet of Things coming out, and people are starting to build for many different types of data, we start seeing different types of data being generated not just by humans, but by machines, by platforms, by cell phones. This is not new to many of you. You are all probably already starting to build out your data platforms or well underway. In the next year, Gartner predicts there will be 6.4 billion connected things that will be generating data. And this leaves us all with the ability of having to build platforms that can store this data, can make it relevant to the business, and can get us to the quickest time to insight as to what that data is trying to tell us for how we run our businesses. The impact is key. So as you have these massive amounts of data coming in, you're going to have data spikes. People need to consider multiple things. And scale is clearly one of the first things they consider. When we're talking about systems at scale, we're talking about systems that can scale just by adding physical nodes and can redistribute data for you across physical nodes. Key also is that when you're scaling, you are making sure that the customers are not seeing any downtime, And many customers, when they are designing their IoT platforms, find that standard relational databases don't meet their needs. They need to be able to store different types of data. They don't want to normalize the data before they store it. They have a need for availability overall, and that they tend to trade off consistency for availability because their platform cannot seem to be unavailable to customers. A good example of this would be Riot Games, who needs to make sure that their gaming infrastructure is always available. People should never see a downtime. Now, for many customers, they're not just looking to minimize downtimes. They're also looking to make sure that upgrades can happen in real time, that systems don't need to come down when they're doing their upgrades, and that they can manage and redistribute their data without downtime. Standard relational databases don't support them. So for them, it's not just about the scalability, it's also about the availability and the resiliency of their systems. And NoSQL databases need to make sure that they not only can handle the peaks, the magnitude of the load, the volume, they need to be able to make sure that they are resilient, that if a node fails, that the cluster of the database is still available, still serving data, and the customer has perceived no downtime. When they need to do an upgrade, they need to be able to do rolling upgrades such that their system is able to handle two different versions of the software at the same time, continue to serve data at the rates it needs to, continues to write data at the rates it needs to, and emphasizes above all availability of the systems. Now this has a large impact across not just the software developers that are defining the systems, but your DevOps teams play a key role in this as well. The DevOps team is responsible for ensuring that the systems have that resiliency, they have the monitoring so that alerts are sent out when they need to be able to react to issues, but that a system can degrade gracefully. And all this is ensuring that the CAP theorem, which states you can either have consistency or you can have availability, forces people into the choice that they're going to need availability over and above consistency. And this is kind of how distributed systems are built. So the art of a distributed system is really about ensuring that you have a system that has that health and resiliency, that it can bring itself to consistency, and so that it is an eventually consistent system. And distributed systems need to talk to each other through APIs. APIs are key to building distributed systems. React was built as a distributed system. It is open source as well as enterprise. React was based on the Dynamo paper that was published by Amazon in 2007. The lessons learned in the Dynamo paper emphasize that availability, reliability, and scalability are key for an eventually consistent database. We have built React as open source, and key to the open source product is something we call React Core. And React Core is responsible for a number of things. React Core has a couple of components in it that are key for the availability and resiliency. The gossip protocol. So if you haven't seen it before, I should go back here a second. React is a ring of physical nodes. Laid out across those physical nodes are virtual nodes. And classically, we recommend that people have minimum of 5 physical nodes in production and 64 virtual nodes across those 5 physical nodes. Now, as we all know, partitioning happens. Networks aren't perfect. Sometimes a node is unavailable, and it's not always due to the network. Sometimes it's due to the physical node. And so these virtual nodes support a couple of components. A gossip protocol. Gossip protocol is where the virtual nodes tell each other the following nodes are available. And this is the layout of the ring, as I understand it. When 2 nodes don't agree about the layout of the ring, the gossip protocol helps them resolve what is the correct layout of the ring. When a physical node is actually removed from the communications with the rest of the cluster, hinted handoff takes place. And a claimant takes charge and says, oh, this node is no longer in the ring. We're going to have to redistribute the data that was on this physical node. So hinted handoff is the ability of a claimant to tell the virtual nodes that still own the data to replicate the data to other nodes. And let me take a step back here. In React, we strongly recommend that the customer use no less than a replication factor of 3, which means whenever a write is taken, the write happens, and then it is replicated 2 more times. If a node goes down, you still have 2 copies. This is configurable. Customers can determine whether they want a replication factor of 1, or, which is not recommended, obviously, or they want to go up to a higher replication factor we have seen as high as a replication factor of 12. So the hinted handoff protocol, again, that claimant takes charge. It takes a look at where the data exists, and this is called the coverage of the data. And it tells the virtual nodes that currently own the data that are still live where to pass the data off, so we get back to a replication factor of 3 without the node that had failed. When that node rejoins the cluster, hinted handoff takes charge again and tells the node that had taken over control for the node that had failed to pass the deltas back to the node that failed. So a natural redistribution of data to maintain the replication factor is key to ensuring that a cluster retains health and can get back to resiliency. Another part of React Core is called read repair. Now, since we have a replication factor of 3, it's possible that a node does not have the current version of the data. Again, this is eventually consistent system. Read repair allows on read for the core to understand when a node does not have the current data and help it to get the current data. So read repair is a detection mechanism for when the data on a specific vnode is out of date and gets it back to the correct version of data. Another good example of resiliency. And then the last component we want to talk about in React Core is active anti-entropy. And this is a background operation. And active anti-entropy is another component that determines when data is out of sync between replicas. Active anti-entropy relies on the hashing, the consistent hashing that we do for each object that's stored in the vnodes. And it maintains a Merkle tree of those hashes across all of the nodes. When it determines that an object is not up to date and its vector clock shows that it has an old version of the object, or bit rot has happened, it then recognizes and ensures that the correct version of the object is then stored on that node and virtual node. Core components to making sure that we have the resiliency and the ability to restore the data to the correct version of the data and the correct object and contents of the data. Multi-cluster replication is also key. This is part of our enterprise product. There are two ways to do multi-data center replication, and many people also tend to use multi-cluster replication in the same data center. A good example of that is a customer that has extremely high workloads and extremely high read loads. And they find to be able to support those extremely high loads, they want all the writes to go to one cluster and all the reads to come from another. This allows them not to have an even larger cluster and spend more money on physical boxes, and it allows them to control their costs. So multi-data center replication can be within a data center, it can be across data centers. We are currently working on policy-based replication, which allows customers to set policies as to where data can be replicated. And this is very important for many customers, especially in the EU today. So we talked a little bit earlier about React Core services, which include the replication and synchronization. It included active anti-entropy. We also have and all of this was built for React KV. So React KV is a key value store. Last year, we determined customers needed more of a time series store. So we determined that we delivered a time series opinionated version of React KV. And we added on the ability for customers to use SQL, a subset of SQL, to create tables, to query, to define their data definitions. So customers can use many of the same tools that they used in an RDBMS on an eventually consistent store. So React.ts is another store that we have introduced. It is using the React Core services, leveraging that resiliency, that scalability, and the ability to regain health. And on top of that, we also introduced additional tools that many of our customers were delivering with their data platforms. So we have introduced a Spark connector, so customers can use their Spark clusters. They can connect directly to the React cluster without using Zookeeper. And the Spark cluster, our Spark connector allows the Spark cluster to be decoupled from React KV and React.ts and be managed separately. But it's a smart Spark connector in that it determines where the data lives and has fast reads and writes through the Spark connector into Spark. We also delivered a caching solution. We heard from many people that Redis is great for caching, but has some problems with retaining data and can sometimes reach out-of-memory issues. So Redis is a great opportunity on the front end on top of React KV or React.ts as a solution for caching. In that case, we have a version of TWEM proxy that facilitates that integration. And then we also have Solr for search, which runs on React KV. And for React.ts, we introduced range queries and a SQL query solution. So customers can use a subset of SQL to query React.ts as well as do range query reads, aggregations, and that is facilitating their time series set of work. So at Basho, we've prioritized the needs of the enterprise. Depending on your case, you may find that you use both React KV for key value store, and in that case, the objects are opaque to us. And some people may say, I need to actually have DDL, I need to have time, I need to have time definition, I need to base my data on time. I need to be able to use queries to access my data, and they have those use cases as well. KV is great for storing any kind of data, is often used for user and session data, product catalogs, healthcare data. TS is great for IoT and metrics data. Other time series data, like storing weather, tides. We've had people storing air quality information, financial and metrics information. We want to make sure that all these solutions are helping you to build the right data platform and helping you to build that in a manner that the data flow allows for the scalability and the resiliency that you need, that the database gives you the availability and scalability that you need. So KV is a powerful solution, and it is open source. And I'm going to diverge here a little bit and talk about the history of open source, because it's very important when you consider open source. I think the argument of open source versus enterprise is pretty much over. In the 1990s, it wasn't. We had 90s, we were introducing operating systems, we were introducing browsers, we were introducing the beginning of some languages being open source like Java, we were introducing platform utilities such as Search, which is supported by Lucene. We moved into the early 2000s. We saw additional platform solutions. We saw many more operating systems. We started to see platform solutions for object management. We started to see solutions for application frameworks such as Spring. Solr is another search solution built on top of Lucene, which is an open source search solution. We also started to see in the early 2000s the open sourcing of virtualization. So Zen, a great hypervisor that's used by many cloud providers, including AWS. The open source of Zen was key to virtualization becoming ubiquitous as well. In the 2000s, we started seeing a lot more DevOps tools, in the later 2000s in the DevOps tools, and we started seeing additional languages such as Go and browsers such as Chromium, and we started seeing NoSQL databases being open sourced. In this century, enterprise is fully embraced open source. It's not just the community that is going to help and make the open source utilities better, but now enterprise has figured out I can get better partnerships, I can actually start to drive my business through open source, and I can get much more productivity by building a community that contributes and makes the product better. Companies like Google and Facebook were quick to embrace open source. And most recently, the companies that some of us thought would be last have been jumping on the bandwagon. Microsoft, Walmart, they're open sourcing their own utilities as well. So, as we build out data platforms, many of us are choosing the open source application toolkits. Akka is a very good solution for Java implementers that want to actually start having a language that has a little bit more resiliency built in. As we mentioned, Redis is great for caching and some store. Kafka is an excellent queuing system, and that was originally open sourced, I believe, by Facebook. Mesos is a great deployment system and allows you to start managing capacity across your nodes, your data centers. It looks to be able to make sure that capacity across nodes is well understood and you're getting more utilization across all of the nodes within your data centers. And so many people start out using React with open source and move on to enterprise when they find they need to use the multi-data center replication. Both are very useful. And at this point, I'd like to start to turn this over to Matt Davis, who I believe may have actually started with using the open source, but he'll let us know.
Cool. Thanks, Heather. That was a great overview of React and everything that that React does. I want to talk a little bit.
Hang on, Matt.
Okay.
There you go.
Okay. I want to talk a little bit about what OpenX is before I dive into how we use open source and how we use React KV. If you're not familiar with OpenX, we are a advertising technology stack. We are a company that sits in between the publisher and the advertiser. We have a lot of focus on the publisher. We call that supply side platform. We are the only independent SSP that's operating at scale across the globe. And all of our SSP products are informed by the technology. We have a large feedback loop that brings in the events, brings in data, and actually feeds automatically right back into our serving systems to provide this kind of automated way to put ads on your publication. We call this entire, yes?
Sorry, we're not seeing your screen.
Oh, okay.
Thank you.
Here we go. Is that okay now?
Perfect.
Okay, so as I was saying, we are a supply-side platform. We're an independent one, and we rely on automated technology that we must have available at all times. It needs to be resilient. You know, we want to, at OpenX, we're maximizing competition because we believe that the market is a market. We don't want to be some kind of behemoth advertising giant that's your only option in terms of publication or advertiser. It's the principle of our ad exchange. We're also really dedicated to good quality traffic and advertising. We don't want malware to show up in ads that OpenX serves. We don't want ads showing up that don't belong on your publication. We work really hard to achieve these ends so that both sides, the publisher and the advertiser, and in fact, the entire audience that's actually browsing the websites is a lot happier with the overall advertising solution, and they're not as annoyed by ads as I think we probably all are at times. So as I mentioned, we're a global company. We operate at scale. We have data centers in the US, we have data centers in Europe, and we have data centers in Eastern Asia. And all of these data centers are interconnected. They all share data. They all feed data into each other, and they all feed data, as I was mentioning before, in this feedback loop that helps inform the front-end systems about what to serve. We achieve all this not only through our own bare metal hardware data centers and our own provision networks, but also through open source distributed technology. A lot of the stuff that Heather's already been talking about. So just to mention those names, React, Hadoop, Erlang, Kafka, Spark, Mesos, we use all of these technologies in all of our data centers to assist in this feedback loop, to assist in making things highly available and resilient. So in these systems, we're talking about billions and billions of keys in our key value store. React KV is our key value store of choice. And we have dozens of terabytes of data in React. We also have dozens of petabytes of data in our Hadoop systems. We have hundreds upon hundreds of Erlang nodes. We have several different real-time data pipelines going through things like Kafka, Spark, and Erlang. And all of these things contribute to these large feedback systems. And all of this combines to serve billions and billions hundreds of billions of programmatic ad requests per month, several billions per day. For those reasons, we absolutely have to have a system that's always available. We always want your web page to load. That's a really important part of what we're talking about. We don't want the ad to be the reason that your web page gets slowed down. We want to be able to serve that ad, and we would rather have that ad be available than a system go down and you get something that we call a blank ad. So just, a blank box on the browser page, right? That's one of our challenges, is being able to really make our global application available at all times. One of the other challenges that we have at this entire scope of really global serving is that traffic is always increasing. There are so many people in the world that are browsing the web. Sure, maybe that's a finite number, but we have more and more publishers coming online. We have more and more possibilities in ad exchanges and advertising networks that want to connect with those publishers. And it's really important for OpenX to give those publishers the ultimate opportunity to monetize exactly what they want in exactly the way that they want to do this. Now, to do all that under the umbrella of globally available and resilient, we have a very complex architecture. We have a lot of complex relationships between all these different parts of those open source products that I mentioned, and they're all interconnected. So sometimes the biggest challenge for OpenX is not necessarily that we understand how React works, we understand how highly available React is, we understand how not highly available other things are, but really how they plug in together. And that's kind of the challenge that a lot of companies face is, okay, well, yeah, we can choose this product, and this product, but how do we really make them work together? How do we build services out of these applications instead of just treating them as, applications in their own silo? So let me talk a little bit more about the different kinds of use cases that we're now using, specifically now with React KV. We actually do use, and I wanted to mention this, we actually do use React Core on its own. And we started into using open source software about 4 or 5 years ago. And actually, OpenX itself, if you've been around a while, you know that OpenX started out as an open source product. That OpenX advertising open source product does still exist out there, but OpenX has evolved. We've evolved into this more enterprise-focused, publisher-focused company. And so what Heather was talking about with enterprises, really adapting these software solutions, these open source solutions. I mean, it's been the key to our success because we're not wasting a bunch of money. Not that we aren't spending money, we definitely are, but we're not wasting money on big monolithic enterprise systems like we did in the old days. So speaking specifically to React KV, what you're seeing here are some bullet points of a few of our use cases for React. And if I had to characterize how we use React in one way or another, we use React KV especially the most in our serving layer. It's an integral part of our delivery system. In many ways, you could call it the backbone of our delivery stack. I mentioned our Hadoop systems and our reporting systems. Those things are definitely important. I mean, they do a lot of the number crunching. We have a lot of MapReduce going on, a lot of yarn types of things going on the Hadoop systems. We even have HBase working in the background doing things. But eventually, a lot of that stuff ends up right back into the React KV clusters. And we have some very large clusters. One of our largest clusters is that first bullet point, our audience, we call it audience enrichment. And audience enrichment is basically a way for publishers and advertisers to be able to meet in the middle on the types of demographic that the advertising is shown to. And this isn't evil at all. Let's not. I don't want to. I don't want to make you think this is kind of some kind of Big Brother evil thing. We're doing things like, I only want my ad to show to people in the Western U.S., or I only want my ads to show to people in Europe. Those kinds of decisions are what audience enrichment is all about. And those are very, very large clusters. And in all of these cases, all of these clusters exist in every single data center across the world. And like I mentioned, they're all interconnected. And many of these clusters are interconnected with the React KV Enterprise product, which has that multi-data center replication feature. And that's really, really important, especially for our global customer configuration metadata. That's how our publishers can configure all that enrichment stuff. That's how they decide this ad network is going to be using this type of ad unit. This ad unit is only going to show up on this thing. I only want these ad units to be served a number of times per hour. Those types of things. I only want to spend this much money within a certain within a certain hour if you're an advertiser. All that kind of stuff, what we call programmatic advertising, is available through these configuration metadata systems. Moving on, I mentioned ad quality and traffic quality. That's our #1 top priority at OpenX when we talk about the advertising networks that we work with and the ads that we end up delivering to the end user, to all of you. All of those systems, especially the quality systems, are also interconnected, so that when you move between regions, or the audience enrichment includes different regions, we can include all of that good quality data between those different data centers. In addition to all of that, intelligent forecasting, that's an example of something that connects very directly into our large big data Hadoop systems, doing a lot of intelligent metrics so that you can look at your ads and think, oh, let's serve this kind of ad because I see a history of this ad being successful on these certain types of pages in my publication. We also use event counting, and a lot of people use React KV for this. There's a lot of examples out there of folks doing this, and this is another one of our systems that I would call a data pipeline. And React KV is an essential part of this data pipeline. It is the delivery part of this pipeline, but this pipeline also includes Kafka. It also includes Spark streaming. We're investigating ways to use our Spark streaming connected with the React data platform Spark. And I can't forget, lastly, not React KV, but a product that Basho makes that's built on React KV, and that's React S2. React S2, if you're not familiar with it, is the quote-unquote Amazon S3 clone. And it is basically exactly that. It is the Amazon S3 API built into the React S2 application that runs on this widely distributed system. So what we're able to do is deliver essential pieces of our delivery stack, referential systems, things that our delivery front ends need to look up very, very quickly. We can deliver all those documents all over the world within seconds with our global React S2 document store. So that's kind of the overview that I had for OpenX. We found React to be a very well-oriented system to what we do, especially in terms of its resiliency, in terms of its high availability. When we lose nodes, we don't have to wake up in the middle of the night. We can wait till the next morning to fix them. When we suffer network partitions, and those happen all the time when you run your own data centers, and when you run your own networks, or even if you're on Amazon and they lose a region, those network partitions are something that React deals with extremely well. In fact, I would go so far to say that among all of our distributed systems, React handles network partitions the best. So it's something that we really love. We have hundreds upon hundreds, almost thousands of systems that serve all of our big data, and React is a huge part of that. Heather, should I send that back over to you?
Sounds good. Excellent. Okay. So I'm just going to take this back to the top. And Dave, do we have any questions?
We do, of course. First, I'd like to remind everybody that, if they want to have a question answered, they can type it into the panel, hit submit, and we'll, again, get to as many as time allows. The first one is for Matt. And Matt, somebody wants to know, from your presentation, it sounds like you have an excellent working system. They're curious to know what challenges you're still facing in terms of scaling the applications and what technologies you're evaluating to address those challenges.
Well, I did mention that traffic is always increasing. Publisher, we kept getting new publishers. We engage new ad networks. So, we have to look at how our customers want to use our systems. One of the good examples of that is our quality systems. We started out using ad quality really kind of as an experiment. We're like, well, let's do this. And so really quick, our ad quality system exists of a scanning network. We actually go out and we look at a publisher page from a browser, and we automatically look at the ads that would show up on that browser in what we call a bid. And in the ad tech world, bid requests go out, and a bunch of different advertisers will bid on a spot in the page to put their ad. And we have to make sure before we ever serve that ad is good quality. So one of the biggest things that we do to scale systems is work as a team. We have to work as a team because we have to understand both the scale of what we're doing on the data side and the scale and the operations of what go on the application side. So to give you a better example, when we were scaling our ad quality systems, we weren't as efficient on the application side as we needed to be. We would have had to scale our clusters to 200 or 300 nodes, which isn't, impossible, but that's a cost. And we want to try to make our cost to efficiency ratio as low as possible. We want to have them as equal as possible. So, it was a lot of working with Deb. It was a lot of working with the team, going, how can we reduce the operations per second on React at the application level? How can we introduce some caching at the application level? We have several different layers of quote-unquote microservices that our events and our calls come back through. Can we optimize each of those levels until we get down to the React system? And by the time that we did this, that we worked as a team, operations and dev together, we were able to get operations per second down, and we were able to greatly reduce the cluster scale so that it was, still pretty large, but we were using the resources much more efficiently, spread out between not only the data layer, but also the application and the front-end serving layers. So that, the whole system kind of eats up the capacity all together instead of like lumping all the capacity on one or the other. I hope that answers the question.
Yep, that was excellent. I appreciate that. Okay, we have a question for Heather, and I'm going to read it now. It says, Heather, you showed a slide with a latency measurement. Our company is just beginning to distribute our systems to physically far apart locations. Latency is a huge concern in terms of performance and reliability. What tools do you use to measure latency and other network node-to-node metrics? Are there any open source tools to measure those metrics?
Great question. So latency across data centers, we have yet to find a good open source tool for that. We've had to build that ourselves. We do in our performance testing within clusters and across clusters, we obviously use tools to capture the information, both the network latency as well as the IOPS latency. There we have a tendency to use Grafana for the visualization, and we are starting to use ReactTS as the database that is feeding Grafana. So that is something that we've done. We have used Graphite as well as the database. The ability to measure latency across data centers is key, but at that point you're also testing the internet and you're testing the providers of the internet. There are tools to just test specific pings available, pretty widely known, but I think what you're bringing up is the need to have tool sets to test, as Matt said, the data pipeline. And I have yet to see those tools exist, so we have had a tendency to build our own. You will see soon that we may start to open source some of our automation for our performance testing. But I'm going to ask this question, Matt, do you have any tools that you have seen and appreciate and think are very useful for testing across data centers?
Yeah, for sure. You mentioned Grafana. That's one tool that we're using heavily. Grafana is great for looking at our metrics from every single vantage point. Grafana itself, though, is just a visualization. You have to really be able to get your data from different points. So there's a product called Thousand Dyes that we are evaluating right now, and Thousand Dyes is a product that's not open source, but it's helping us. It's kind of like a smoke ping kind of thing. If you're familiar with smoke ping, it gives us a better visibility into our networks. Now, I mentioned earlier, OpenX specifically, we have private networks, so we don't do a lot of our intra-data center communication over the internet. When we're talking about internet serving, I would say it's not only important to be able to measure your latency, but to understand where your latency comes from. And that's why it's important to be able to gather metrics from every single layer of your serving delivery stack. And that's what we do, and that's how we really utilize Grafana, is we can build metrics. How long does it take this command to go through? How long does it take for this request to go to this layer? How long does it take for the next layer to hit React? And how long does it take for React to return the data? We have all of those kind of statistics in Grafana, so we can fairly. Sometimes it's difficult, but we can usually see at what layer we're suffering bad latency.
Excellent. Okay, I guess we'll start with Matt on this next question. Someone wants to know how you use Apache Kafka, and can you give a good use case?
Yeah, sure. We have Kafka running in a few of our use cases, actually. A couple of that I mentioned in my slide are the ad quality data pipeline and our event counting data pipeline. So I'll talk about the ad quality one first. Our ad quality pipeline we feed all events, and actually I can talk about both of them at the same time. A lot of the serving layer collects events, and those events are all kinds of things. What browser you're using, where you're located, what region of the U.S., what site you're browsing on, all different kinds of metadata. How many times a certain ad has been served, how many times a certain publisher has done this or certain advertiser has done that. Those are all events that we capture, and those events are what end up in Kafka. We have LWES is one of our transport technologies, and we have LWES listeners at the top of our Kafka stacks. And those LWES listeners receive all of these events, and we put those events into Kafka. That way we can read events from Kafka, and we do that in a couple of ways. Like I mentioned, we use Spark. We also use Storm in some of our data pipelines. But whatever your middle layer computation system is, we're able to use Kafka to pull events, but also, and the cool thing about Kafka is if we have an outage in our computation layer, we can go back and we can replay events. We can reset the offset in Kafka and go back and get events if we missed them. So that's just a couple of ways that we use Kafka.
All right. This next question is for Heather, and the question is this: there are many, many NoSQL solutions in the market, as we know, and since there are many solutions, how do you suggest developers evaluate them to choose the right one?
Good question. And we've been through this before at GoGrid and Mashery when we needed to choose NoSQL solutions. We started with a common technique, which is called a proof of concept. And in a proof of concept, you basically define your goals. Key goals that really should be done are goals around not just the scalability, but the resiliency and the availability. So part of the proof of concept is running tests. And so many people start out with running performance tests and scalability tests. But prior to getting to those tests, if you've actually written your goals down, your goals should be inclusive of not just the technical needs and the data pipeline needs, but it should also include how active is the community, how easily can you get support for it, how many books are written about it. This gives you an idea of where the technology is in its life cycle, and it's important that you do have a strong community behind it. Now, getting back to the test portion, we strongly recommend to folks when they are doing their proof of concepts that they run a minimum of 3 tests. The first is to test the performance for both reads and writes. They need to think strongly about where they believe their load will be. There are some folks who believe their write capability is more important than their read capability. There are some folks who believe that their read capability is more important than their write capability. And then most of the folks are in between that, where they believe they need to have both read and write. And so understanding what the requirements are for the levels of the read and write are key. Once you've done your performance testing, you want to repeat that performance test and add on a test for linear scalability. So add in a node. How long once the handoffs are done and the data redistributed around the ring, how long does that take? And does that mean once the ring is stable again and the handoff is done, did you scale linearly? And can you increase the load that much more? And you want to see, and you want to graph that out, and you want to capture all that data, graph it out, and make it sure that you do see it a linear scale. And very important is running that same set of performance tests and doing a resiliency test. And in the case of a resiliency test, you have fully loaded data, you have the load running again, your performance test running. Now take a node out of the ring. There will be some higher level of traffic around the node because you've got the hinted handoff going on. The data is being redistributed again. You have less capacity. And you want to measure how long it takes for that hinted handoff to complete, and you've reached a stasis level of just the performance tests running again. That is very important for you to figure out how long will it take if one node fails. And if you, for extra credit, continue that resiliency testing and see what happens when 2 nodes fail. That will prove the point of Matt's, can you sleep through the night for this or not? And sleeping through the night is a wonderful thing to do. I think those 3 tests in a proof of concept are key to be able to evaluate properly.
Heather, if I could just add on something to that too, when you're talking about a global infrastructure, take that test one step further. See what happens when you shut an entire data center off. What do you have to plan for when you have to shift traffic from one data center to another? Are your clusters in the other data center scaled out to the point that they can handle the additional traffic that you've redirected from the data center you turned off?
That's a great point, Matt. And you're probably using something like Ultra DNS or Dyn or something like that to make sure that the failover happens in a timely fashion.
Yep, we actually use NS1 is our DNS provider.
Excellent.
Great. All right, I see we're running right out of time. We're up against the clock, but I'd like to throw it back out to Heather and Matt for one, last wrap-up of perhaps a final thought, about 30 seconds. Heather, we'll start with you. What would be the key takeaway for someone from your presentation today?
That you want to make sure that you're setting your team up for success as you build out the data pipeline. That success, as we said before, is not just about scalability and performance. It's about the resiliency and availability.
Great. And Matt?
Yeah, I would actually expand on that very topic. When all is said and done, it's not just about how the technology itself works within your use case, how your specific architecture operates. It's also how it gets operated. It also has to do with the people. It has to do with training people, documenting things well, and being able to trust your systems so that you can keep things up and running.
Great. Thank you very much. All right. I'd like to thank our attendees for hanging in there with us today. We certainly appreciate their attendance. I want to thank Matt Davis, Senior Site Reliability Engineer at OpenX, and Heather McKelvey, Vice President of Engineering at Basho Technologies, for their participation today. Of course, we'd like to thank Basho for sponsoring this event today. And again, I'm Dave Rubenstein. You can look for this on sdtimes.com in the next day or so. And until the next one, so long, everybody.
Thanks, Dave.
Yes, thank you. Bye-bye.